Today I have the pleasure to introduce Enora Tourneur. She holds a master's degree with specialization in exploration and geomatics of mineral resources from the University of Orleans, and last year finished her PhD at University of Montpellier, with collaboration with a Morocco company about fluid circulation around crustal faults in Morocco or deposits. Today, she will bring us insights about how hydrothermal and structural features control the Bou Azzer cobalt-nickel ore deposits. Stay tuned with us, and the next 20 minutes are yours.
Thanks all for being present to this talk. So effectively, the Bou Azzer deposit is a mine of cobalt and nickel, and I will present you its mineralogical, textural, and structural features in order to discuss the hydrothermal and structural control of mineralization. So I want to thank my collaborators here, the Laboratory of Geosciences Montpellier, the management group who allows me to do this PhD, this thesis. So the Bou Azzer Hill is located in the central part of Anti-At of Morocco. The Anti-At follows southwest northeast orientation and is composed of several linears separated by a major fault of Anti-At, as we can see here. To the southwest, we can find Paleoproterozoic rocks ages which compose the linears, and in the northeast, you can find linears with Neoproterozoic to Cambrian rock ages. So the Bou Azzer linear is composed of different rock units. First, a Paleoproterozoic basement, thanks to gneiss and orthogneiss here in brown, and an ophiolitic complex, which is supposed to be a Neoproterozoic suture zone. We can see here in blue and in green, and a volcanoclastic unit, which are overlying all units in pink here, and it's called the Warzazal supergroup, and a sedimentary cover sequence, which ages between the transition with Precambrian and Cambrian ages, as we can see in white. So the hill here has a great diversity of mining exploitation. We can find to the south the Bleda mine, gold mine here. And we have also several copper occurrences in black here in the Cambrian sequence. And but I will focus my presentation on the cobalt nickel district, which is exploited in several mining centers, especially located in the west part and the central part, when they are surrounded by quartz and serpentinite. So just to remind you, there is two types of structures which are exploited at the Bou Azzer mine. This general model was presented by Maasha and collaborators in 2012, and we can see a massive mineralization time, which is elongated massive ore bodies composed of nickel, cobalt arsenides, and it's hosted in a carbonated and siliceous gangue between the Warzazat supergroup, serpentinite, and quartz diorite. We can, a vein system is also exploited, and it's a vein cross-cutting all units, and they are only mineralized when they intersect the massive mineralization. So during my PhD, I wanted to establish relationships between texture, deformation, mineralogy, and geochemistry of the fluid and the mineralized structures. I wanted also to build a global model of mineralization formation and discuss the geodynamic implication of the mineralization emplacement. For that, to answer the question, I made 7 weeks of field work, in the Moroccan Bou Azzer ore deposit, using after Petro-structural 2D and fluid inclusion analysis in the University of Montpellier, Geneva, and in collaboration with Hantsche and Kenin Kunzmanov. And after I made a geochemical study of fluids and mineralization using the laser ICP-MS at the ETH of Zurich. So to start, I will present you the fluid geology petrographic study. So the massive mineralization are massive elongated ore bodies composed of cobalt and nickel arsenide, especially. They are hosted between serpentinite and the siliceous gangue, and the major part of the gangue is composed of carbonates. We can see an orientation which is east-west, and which is the same as the Bou Azzer in here. So about the paragenetic evolutions, the petrostructural study allows us to see 3 stages of formation. The first start with the nickel arsenide-rich stage, with the formation of nickeline and Ramelsbergite, especially in the serpentinite gangue. After, we can see the formation of a cobalt arsenide-rich stage with massive and scuteridite, as you can see here with bounded growth. It's really spectacular. And to finish, we have a iron-rich and arsenic stage with the formation of lowlandite, especially, which forming during the formation of carbonated gangue. And here you can see it's on the edge of a sapphirite, another cobalt arsenide mineral. Some textural features were observed, and they are really interesting. We can see a brachiated massive mineralization texture called BMM and a laminated massive mineralization texture called LMM. This brachiated massive mineralization texture is seen in the carbonated gangue here, and we can see a dynamic environment of the formation of this gangue. And the laminated texture is observed thanks to the nickel arsenide lamination and the carbonate also. So the second structure, which is exploited in the Bou Azzer mine, it's a vein system. They are structures with normal movements seen by the polar part structures. These veins are composed of cobalt and iron arsenides, quartz and calcite. On the horizontal plane, we can see dextral and sinistral movement, which are consistent here with northeast, southwest shortening direction. So we also saw during the fieldwork third structure, which is exploited, and this is large pocket composed of very large chrome quartz and rhombohedral calcite, as you can see here. And it's also composed of cobalt iron arsenide fragments, but no nickel arsenide were observed during the field geology in underground. And also no evidence of motion is observed in this bucket. It's only extensional texture. So the vein system and the pockets have the same paragenetic evolutions. And we start with a cobalt arsenic rich stage with the formation of hexagonal and tiny scuteridite. After, we have the formation of cobaltite, so sometimes around scuteridite, but also is isolated between chrome quartz. At the end, we have the formation of lowlandite, which is related to iron stage. You can see here as a really shaped forms. And this lowlangiate is associated with the carbonated the gangue of the veins and the pockets. So I made also fluid inclusion analysis, and I saw two types of fluid inclusions mainly. So we can see in the three types of structures the combination between three vapor liquid highlight fluid inclusions, as you can see, associated with single phase gaze inclusions here. And we saw that it can show the evidence of boiling in the three types of structures. And we also saw a very strange combination of single phase gaze inclusions here in black, and the presence of single phase of crystal of highlight inclusions in the gangue of calcite gangue of massive mineralization and pocket. So there is no vapor or no liquid, only NaCl, very large inclusions in this gangue. So after the geochemical study of the mineral and the gangue was made in the arsenide, the spinel, in the carbonate gangue of all the structures also, and in fluid inclusions. So here I present you the major results that I obtained. So you can see in the arsenide and spinel a negative correlation between nickel and cobalt. We can see also in carbonate and spinels positive correlation between sodium and potassium, lithium both in the carbonate and in the spinel. And in the fluid inclusions, we can find also some positive correlation between the gangue minerals, the spinel, and the fluid. So this same signature we try to interpret this signature with implications, the impact of the hydrothermal fluids who can control the formation of the cobalt nickel ore deposit, because we saw the same signature with the positive correlation between all these structures, the fluids, the carbonate, the spinels, and the arsenide. The laser ICP-MS analysis allow us to make the study in the fluid inclusions. Two hypotheses of the origin of fluid are presented by the scientific community. One seawater evaporation sources, and another magmatic signature of the fluid. So thanks to this reference line made by McCarthy and collaborators, we can see that how fluid inclusion follows this line, which correspond to the seawater evaporation made in large data in Jurassic water. So we try to say that the fluid of Bou Azzer who could precipitate the cobalt nickel ore deposit has seawater evaporation signature, as observed in other analyses such as Estaraj and collaborator in 2005. So to resume all this quick presentation of the Petro-structural study and the geochemical study, I tried to do a general model of the Bou Azzer ore deposit. So in the first stage, stage A1, there is a serpentinization of the ophiolitic mantle of Bou Azzer. This serpentinization, here we can see in the gray, light gray, can release the iron of serpentinite to form magnetite. And this magnetite can concentrate some cobalt and nickel iron elements which compose the serpentinite. In stage 2, thanks to our textual and Petro-structural studies, we saw The combination with so the LMM and BMM textures, the laminated and bracketed texture of the serpentinite gangue. And we try to say that the exhumation of this serpentinite or normal fault observed on the field work can lead to the formation of a serpentinite breccia in an extensive environment, as suggested by the little spot here. So we try to think about the passage of fluids that can leach and release nickel, arsenide, cobalt in the environment, thanks to the presence of magnetite, chromatite, and spinel observed during the Petro-structural study. After the stage B, represent formation of the cobalt, the nickel cobalt mineralization. As I could show you before, by the in situ spinel remplacement of the relics of spinel observed in the serpentinite. So thanks to the leaching of the mineralization, the spinels and chromatite, we can form the cobalt nickel mineralization. And we think that the fluid enriched with metal and maybe NaCl, if you remember, we found NaCl fluid inclusions, can allow the formation of cobalt nickel mineralization, because it's a strong, it can complex very easily with these elements. So after in stage C, this is what we can see on thanks to thin section studies. There is a carbonation of this serpentinite gangue, because we saw relics of serpentinite breccias, and we suppose it's his full carbonation, and we observe the formation of the cobalt iron mineralization by the leaching and the precipitation of leaching of pre-existing structures, and after the precipitation of the cobalt iron mineralization on the pre-existing minerals. So thanks to fluid inclusions analysis and the microthermometry, we can see a high temperature and strong salinities in this massive mineralization. And finally, the stage D show extensive tectonics, which leads the formation of the cobalt iron arsenic sulfur mineralization into the veins and the pockets. This extensional tectonic can lead after the reaching of the massive mineralization bodies and the formation of the cobalt and iron mineralization inside the veins and the pocket. And we saw, thanks to laser ICP-MS studies, that the outgoing fluid is enriched in zinc with lead, copper, and also NaCl. Fluid inclusions of hydrothermal analysis allows us to show lower temperature and salinity in the veins and the pockets. So in conclusions, what we can say about the Bou Azzer deposits, the Bou Azzer mineralization can be compared to a massive arsenide deposit related to a hydrothermal circulation in a bracketed environment, systematically in contact with serpentinite and quartz diorite. But the remaining question is, what about the 5-element veins or deposit classification? That I know the strong part of the community say that this Bou deposit is related to this type of classification. But even if some characteristic relate this R deposit to this classification, I think that the essential role of serpentinite is underlined by the systematic contact of the massive ore body with this host rock. This massive mineralization lenses seems to be previous bracketed ones with fragment of serpentinite, relic of spinel grains, and they are after leached by hydrothermal free composed of which is composed of NaCl and can complex the cobalt nickel hosted in the serpentinite and precipitate it in this accidental fault between the serpentinite and the quartz diorite. So thank you. Thank you for your attention.
Thank you, Enora, for this really nice talk. Now we are going directly to questions to our panelists. But if anyone has questions, just text on our chat and we will reach after the panelist questions. So I would like to ask directly to Matthias or Charles, if you are any comments or questions for Enora.
Thanks first of all, for this interesting talk. I think there's a huge development since I saw your last talk on Glasgow. In Glasgow, so I'm happy to see that. Lots of more new data. And I think, yeah, you did a good job in kind of improving the research stage on that point. But there are still some points. I think we also already discussed some of them in Glasgow, where I think you should at least broaden your scope a little bit. Yeah, you look at the Bou Azzer deposit very isolated in a kind of a way, what you presented here. And I mean, we know that these types of, however you call them, native metal arsenides or 5-element veins, they occur globally. And even if you find something else, like if your model doesn't agree with the other models, you should show what the others think and why exactly you think that yours is a little bit different. And I think if you start with that, whatever in your current manuscript or in your talks, you would improve your talk a lot, because then you kind of get a nice line of arguments and say, okay, the others say this, and you need this and this to form them, and this agrees or disagrees with my observations, and that would give you a nice intro, I would say. And maybe coming now to my first question, I also have a few other comments, but my first question would be, what is the actual difference between your massive ore and your vein ore?
The difference is the formation, because the veins and the massive mineralization, the vein have some extensional texture inside the veins, and the massive mineralization are only bodies between the two host rock, the serpentinite and the quartz diorite. So it's a difference. So there is also the lower temperature for the veins, but we didn't see extensional. Yeah, we can see extensional texture in the massive mineralization, but it's not related to a veins, big veins. It's really lenses, big bodies put here. I remember during our discussion in Glasgow, we talk you talk about the successive levels of nickel and cobalt and iron mineralization are in the Leblanc work made in 1975, but it's a great job. He talked about also a symmetric formation from the center with nickel and after cobalt and after iron. But during my work, I couldn't see this different levels between the mineralization. So I try to see if in the lower in depth, if I could find nickel arsenide only, and after near the surface only iron. But no, I couldn't see this evidence of a different level of mineralization of stage. So the difference is the veins are really veins, the corroscrete diorite, and it's obviously veins, and pockets is really extensional structures. But the mass mineralization, it's very inside a big bracketed space and full of scuterodite, majority of scuterodite.
Yeah. Okay. I think you should be careful with discriminating between these two types, because when you look at your fluid inclusion data, your vein fluid inclusion data actually is a part of the bigger group that you have on your pockets. So it means they overlap, the data overlaps. So it could be just that your temperatures in the veins are not as high or whatever, could also be an effect of statistics kind of a way. And the Bou Azzer system is the biggest system I've ever visited in terms of 5-element veins. So you have to be careful in terms of scale. Yeah? Like what you're looking here on other and smaller vein systems, you might see these variations on already 10 to 20 meters. I don't expect to have them on a 10 to 20 meter scale in the Bou Azzer system. I expect to have them on a several 100-meter scale. And that's something maybe including
if I can comment that, I could visit all the mining center from west to east of the Bou Azzer, and from 0 to 500 meters depth. So all structures are not only 1 or 3 mining center. It's really 15 mining center and 20 zones. So it's not only related to 10 meters squares. It's really on maybe yeah. If I focus only on one ore deposit, it can be more interesting. But yeah, I try to do a general model with all the informations I had. Yeah, it's really on the big larger scale than 10 meters. Okay.
Did you find methane in your fluid inclusions with Raman?
Yeah, some gas, single phase gas inclusion. I couldn't find methane.
That's interesting. I would have shown that in your like. Why haven't you?
Yeah, I will prepare another paper on it. So I need to work harder on this to be sure it's really good.
Okay. I don't know how. Maybe I'll leave someone else to ask a question or so. I don't know how much time do I have. I would have another question, but maybe later or so. I don't know.
Yeah. Okay. Maybe we are going to Charles because he had a question, and later, if we have time, you can comment again. Thank you, Matthias.
Hi, everyone. Hi, Enora. Thank you. You gave a very, very clear talk there. Some really, really nice diagrams, really well described. It's really good. I think I'm going to echo some of what Matthias has said. I'm not a specialist on this type of system, but I guess what I can do is I can bring in experience from working on systems of mineralization which are slightly less well characterized in carbonatites and alkali silicate systems. And I think that a lot of what you've shown here is relevant at very small spatial scales. And a few people have written in the comments here as well, how does this fit into a larger model for cobalt mineralization? What are the shared characteristics between Bou Azzer and other systems, and what are the unique characteristics? Where does the metal come from? What does this look like if you zoom out to a scale of a tectonic plate or something like that? And I think that these sorts of things, once we start looking at these types of ore deposits in a system scale, where you think, where do the metals come from? Where do all of the arsenides come from? That sort of thing. Are they essential for forming this type of mineralization? And then you put that together with all of the work which you've done here on the fluid inclusions for transporting the metals at the local scale and the ore textures for trapping. I think you can have a very interesting bigger picture and start using that to be predictive and think about where else you could look in the world for something similar to this. Yeah. That's just a comment, really. I don't have any specific questions because I think you gave a very clear presentation. I could follow what you were talking about, but I'm just going to give a comment for. where you might want to look as well.
Maybe, yeah, I can just answer from 3 questions you asked about the metal origin, arsenic origin, and some comparison with other ore deposits, such as Bou Azzer. So obviously, cobalt nickel comes from serpentinite. It's the only earth rock who can have these elements and can allow the formation of this massive mining of cobalt nickel. If you know, Bou Azzer only exploited cobalt as a primary element, not a secondary related to cobalt or nickel, only cobalt. And after you can find nickel and iron, really interesting. The metal origin is for me the serpentinite, and in the serpentinite you can find spinels and magnetite. Chromitite were enriched in them because I saw and I could saw it in laser ICP-MS analysis. About the arsenite, I don't know because arsenite has a large origin from maybe apatite in quartz diorite in water in sedimentary rocks. It's a complicated question because it has a large origin, and to the comparison of Bou with other ore deposits. I couldn't find, and I tried to find the same ore deposit in the world who can relate it to a briquetted serpentinite, quartz diorite near them, or yes, 5 element veins. Classification show a large scale of host rock, so that's why I can't. Maybe the temperature, the salinity are the same, and it's inside the veins, and the elements are the same, the cobalt, the nickel, the silver, and the bismuth. But for me, the serpentinite is too present to specific to use a classification of 5 element veins, because it's really specific to the serpentinite, in my view.
Okay, thank you, Enora. We have another question from Michael Annenberg. Are you able to unmute?
Yes, I can. Hi. Thank you for the talk. It's interesting, fascinating, you know, and cobalt is one of those elements that is really hyped and everyone is talking about now. So it's good to see some more stuff on it. Now I have 2 questions that are maybe kind of related. One, ophiolites and serpentinites are everywhere. Okay, I mean they're one of the more common rock types on Earth. What's special about Bou Azzer and similar deposits in the world to make this kind of nickel and cobalt concentrations? And the other question is, it showed fluid inclusions with 20, 30, 40 weight % of sodium chloride. Where is that coming from? Because it's very unusual to get very saline inclusions of fluids like that in natural systems. Yeah, so maybe you can comment about that. And I think maybe answering that helps answering why do we have the deposits in this specific ophiolite, maybe.
Yeah, ophiolites are very, very common. I know, but I maybe in us, for example, in New Caledonia, we have ophiolite, but only nickel and laterite ore deposit, but no cobalt primary ore deposit. In Oman, you don't find only cobalt ore deposit, mainly exploited for cobalt, or in the north of the Anti-Atlas. There is another. I'm quickly going to. There is another in Sierra ophiolite complex, which is maybe related to this, which is maybe the same method of Bou Azzer. And here I try to find maybe proof to try to think about cobalt ore deposit in Sura of July, but there is no evidence of serpentinite, only metagabo or metamorphic stuff from the mantle. So I know there is a lot of geolite in the world, and but in Bou Azzer we have specific serpentinite and metagabo and basaltic rock crust. But yeah, I know it's strange, but I can find another place who you can find cobalt and ore deposit, such as Bou Azzer. And about the right in field inclusions, as we can see on the analysis of feed, the field inclusions show signature of seawater evaporation. So maybe the seawater concentration of chloride can be strong enough to enrich these field inclusions initial, but there is now another hypothesis about the precipitation and reconcentration of light in the mantle during serpentinization. Some scientific work, and I can send you after if you want, show by experimental studies the formation of only NaCl inclusions in during serpentinization, because they reconcentrate all salt with the heating in the dehydration of the mantle during his serpentinization. So if we suggest that the carbonate found here and here as a result of the carbonation of the serpentinite ancient previous earth rock, it can be possible to find this crystal of salt.
Okay, so then maybe, you know, like one of the ways I could find a deposit like that is to go to an ophiolite somewhere, look for fluid inclusion. Then if I see a fluid inclusions that are very silent, then I can say, okay, maybe somewhere around here, 100 meters over there or kilometer over there, I will find a cobalt deposit. Is that something that you think is feasible?
No, it's not. I don't think it's a good way to do it, but it can be an explanation for the presence of chloride, to be sure. But for the exploration methods, it's not a good way to do, because it's too large.
Okay, good, thank you.
Sorry when I interrupt, but one comment maybe. Most of, or many of examples of 5 element veins are actually not hosted in basic or ultra basic rocks. They're hosted in meta-sedimentary units. So this is not kind of, you can also form them without these rocks. This is just kind of one example where these rocks are closely associated to these deposits.
Okay, thank you very much, Enora. I will pass the word to Aaron.
Yeah, thanks everybody so far. We're approaching the end of this discussion section already, so I want to apologize to anyone who we don't have time to ask your question. But Enora, there's been a couple questions in the chat about the source of both arsenic or the metals. So with that, I would like to invite Saeed Ilman to unmute himself, and he can ask his question about in English.
Thank you, Aaron. Thank you, Enora, for your presentation. You talk about cobalt, nickel, and iron sources from serpentinite. What do you think about arsenic? And the second question, Bou Azzer is known by its gold mineralization. What do you think about this gold formation or paragenesis? Thank you.
So the gold formation was at my my work during my PhD, but if I remember, I will show you the map of Bou Azzer here. The gold, the Bleda gold mine is related to granodiorite, and of the hill here in pink. So I have to confess, the granodiorite is younger than the serpentinite and the quartzdiorite formation, but I think it's related to this granodiorite, and but I can't say more about it. I'm sorry, Mr. Hillman. So, but I think it's related to magmatic formation.
No, Enora, I talk about gold associated with arsenide. Not Blida is known. Blida is a copper mine deposit. There is just a small bite of which exploited gold.
Okay, so
What about my question, the relationship between arsenide and gold at the Bou Azzer or deposits?
All right, so I don't know, because I never saw gold in the cobalt nickel or deposit related to arsenide, so I can't answer your question. I'm sorry.
Okay.
And for the original arsenide, arsenic, sorry, but you can find arsenic in many minerals, such as apatite and such as arsenic can have many origins. So I didn't work on this subject, so because I had a lot to do. So there is so many origins that I can't tell you more. Sorry. And I see all around the scientific community about the arsenic of Bou Azzer. They only mention some origin, but there is no further explanation I didn't find.
And just to give you an idea about this, many authors talk about volcanic lava from Jebel Bou of the Cambrian age. Others talk about quartzdiorite. Others talk about other sources from Cambrian or other. And just to give you another idea about Sirois is also we found some cobalt veins. If you are interested to study them at this area, just serpentinite. This cobalt are not related to serpentinite in the area we found.
Okay.
Thank you.
Great, thank you. Yeah, thank you very much, Saeed and Enora, for your presentation and discussion. There's tons of questions in the chat, and if you would like to discuss them further, you can contact Enora maybe after the talk, but we should move on to our next speaker.
Thank you for the question and discussion. Thank you.